This screencast will introduce you to the S397 GENIE interface. You have hopefully installed the model by now and opened the display in your browser. We will leave the description of the control panel until later in the screencast and get going straight away by clicking the Start button. As we haven't yet changed any inputs, this will set the model running with all inputs at their default settings. This simple experiment is the basis of the first GENIE activity 4.3.1. There may be a delay of a few minutes the first time you do this. This is because the model is downloaded as lines of computer code and your system needs to do some work to compile the program and turn it into an executable application. Now the model is running, we will scroll down to look at the four graphical output panels. The panels on the left are maps of climate variables. The variable plotted is selected from the drop-down menu above them. This gives you a number of different outputs for vegetation, land surface, atmosphere, ocean and sea ice to choose from. The top map is the instantaneous value of the selected variable. This is updated at the end of each month. The values and units are represented in the colour legend below the graph. You can hover over a grid cell to display the grid coordinates and variable value above the cursor. If an ocean output is selected, you will be able to choose the depth level that is plotted. Remember that unlike the atmosphere, the ocean model in S397 GENIE is three-dimensional. These range from depth level 1, the surface ocean layer, which extends to a depth of 80 metres, to depth level 16, the deepest ocean layer, which goes to a depth of 5,000 metres. As you go to deeper levels, you'll see the ocean area shrinking, as not all ocean reaches these depths. The outline of the surface ocean is always visible. The lower map represents changes in a climate variable. These are also referred to as anomalies compared to the initial condition. In S397 GENIE, these maps plot the change relative to June in the first year of the simulation. Let's select ocean surface temperature and follow the change plot through the repeating annual cycle. In December, at the opposite end of the seasonal cycle to June, the ocean temperatures are 1 or 2 degrees warmer in the southern hemisphere, and they are 1 or 2 degrees cooler in the northern hemisphere. This reflects the contrast between summer and winter in the two hemispheres. When the simulation comes around to June, the anomalies are close to zero everywhere. In this experiment, with default settings, the model remains in a stable seasonal cycle because none of the inputs are changed from their default values. You will explore this behaviour in more detail in Activity 4.3.1. When you come on to the later experiments that drive changes in the model, it is important to remember that most of the change in the anomaly plots is due to the seasonal cycle. However, the model stops in June of year 101, and the anomaly maps at this time will be the most useful for your analysis because they won't show this seasonal change. They'll compare June in year 101 with June in year 1. The charts on the right are time series outputs. Once again, you can select from a number of variables to plot. These are air temperature, land temperature, and reservoirs of vegetation carbon and soil carbon in different regions of the planet. The ocean and atmosphere carbon reservoirs are also provided. These data all refer to large-scale averages, for instance an average across the whole planet or across a specific region, and are useful to show how the different outputs vary through time. This contrasts with the maps, whose main function is to show how the outputs vary in space. The upper panel plots monthly averages of the selected variable. This varies through the year, reflecting the seasonal cycle that was also apparent in the anomaly plots. The lower panel plots annual averages of the same variable. You will probably find the annual average time series the most useful one for understanding, as this captures long-term trends in the simulation, which can be harder to spot in the monthly charts. In this particular simulation, the changes in the annual averages are small. Again, this is because the model inputs are set to their default, and so the simulation is in an approximately stable seasonal cycle. If you scroll further down the screen, you will find a summary table of the data that is generated in the annual average time series. You can watch this data being appended as the simulation progresses. Scrolling back to the top of the screen, you can see options to download a PDF of the annual time series, or text files of the monthly and annual time series data. For instance, if you click on Annual Data, a dialog window opens allowing you to download the data file to your computer. Make sure that you save the file to a known destination so that you can find it again later on. If you then open Excel and try to open this file, the text import wizard should open. This should determine that your data is fixed width, and you should select Finish to open the data in a usable format. The spreadsheet may be used to generate graphs or manipulate data. For instance, the module activities often consider the change in some output over the course of a simulation. This could be calculated from the spreadsheet as the difference between the first and last rows. To generate a chart, select two data columns, time and variable you are studying, and plot a scatter chart. You can, for instance, use this to produce a saved copy of the annual time series that is plotted in the interface too. However, this can also be done by the drop-down menu on the top right of each time series chart. Finally, we turn to the question of how to change the model inputs, as required when carrying out useful experiments. Scrolling to the top of the screen, you can click the top tabs to move between the inputs of different modules. For example, clicking the Other tab allows you to specify CO2 emissions. Before doing this, and before starting any new simulation, click Stop if a simulation is still running, and then Reset to ensure that all model parameters are set to defaults. You can set emissions to 5 gigatons of carbon per year by typing 5 in the Emit 0 box, and then pressing Return to set the simulation running. To change any of these inputs, you can choose either to type in the box or use the slider to change the value. If you use the slider instead, you will need to click the Start button to set the simulation running. Now that this experiment is running, you can select the atmosphere carbon chart via the right drop-down menu, and you will see the value climbing through time in response to these emissions. You can explore all of the 4 output panels to investigate the changes to the Earth system that this causes. Think about what questions you're asking when choosing these outputs. This should help you interpret the experiments.